Okay, let's talk about some of the key characteristics of living things. We can see here on slide number 15. So if at any point you're not sure where I am, you can always look at the bottom right-hand corner. It'll tell you which chapter and which slide that I'm on in case you are following along in your notes. Okay, so the characteristics of life include organization. So living things can take what you might think of as chaotic piles of stuff, dirt and nutrients, and organize them into structures like cellulose or collagen, right? We can turn chaos into order, and it is really a unique characteristic of living things. Number two, metabolism, which can be defined as the sum of all of the chemical reactions in your body. What do I mean by that? Well, you use chemistry to digest your food and to absorb the nutrients like blood sugar and amino acids into your body. And then you use pathways, chemical processes, or chemical reactions to build those into your own physical body. That's a part of your metabolism, and it allows you to store nutrients and energy for later on when you might not have enough to eat. When you don't have enough to eat, your body can then begin to disassemble those molecules that you've stored up so that you have both energy and building blocks to live. And that's really what metabolism is all about. Responsiveness, of course, you know this. Living things respond to their environment, they move towards light or away from sound. We have the ability to grow in both the size of our cells and the number of our cells. We can develop, we can change over time. So the first subtype of development there is differentiation. And of course, that is what happens when a generic primitive cell, like a stem cell, specializes to become something more unique, different. That's where that word comes from, differentiation. So after sperm and egg combine, for example, we all start out as a single cell called a zygote. But now, as an adult, I have several hundred different types of cells. And where do they all come from? All through differentiation of one more primitive cell into a more specialized one. That's slightly different from morphogenesis, which is the change in the shape of the tissues or organs. And then, of course, reproduction is a unique characteristic of living things, too, whether it's asexual reproduction, like sponges or microbes, bacteria, or sexual reproduction, which is much more important in terms of the diversity of life. We'll learn all about how sexual reproduction allows us to shuffle the DNA, right? Shuffle the genetic code to create offspring that might even be better suited to our environment. Here's the next physiological phenomenon we need to understand: homeostasis, the ability to maintain a stable internal environment. So there are set points in your body relative to different values, like body temperature. What's the set point for body temperature? 98.6. Is there a set point for blood sugar? Yeah, it's sort of an ideal where our body wants to be. Blood pressure, heart rate, the amount of sodium or chloride in our bloodstream. There are literally hundreds of different values, and these are very much the values that we use to screen for and diagnose disease. In a young and healthy person, there is no disease because the body is able to maintain those set points through a process called homeostasis. So let's talk through body temperature. That's the easiest one to think about. We know that our outside world here in the beautiful state of Wisconsin is not a stable internal environment. It is a dynamic external environment where it can be hot in the summer and cold in the winter. And so if my body temperature begins to rise in the summer, or if I'm wearing too much clothing, my body will detect that deviation. Look, we've gone away from the set point. It will decide to do something about it, and then it'll turn down the body temperature through sweating. Or if we're too cold, our body will detect that we have deviated away from the set point, and then through shivering or increased movement, we generate heat and bring ourselves back up. So those might be two rather dramatic examples, but in reality, this is happening all of the time, right? We're a little bit too cold, a little bit too warm. And so by detecting a change and then exerting a force, we can restore that set point. That's called a negative feedback loop, by the way. A feedback system can be either negative, where it returns us to the set point, or a positive feedback loop where it pushes the value away from the set point. I'll talk about that one in just a second. 99% of the time, feedback systems are negative because the whole point is to maintain homeostasis. So if I'm dehydrated, I get thirsty and I drink, right? Or if I'm overhydrated, my body makes more urine and I am able to get rid of that excess fluid. Nearly everything is a negative feedback loop. There are two examples of positive feedback loops I'd like you to know about: labor and delivery and the blood clotting cascade. So in labor and delivery, obviously labor contractions increase in their intensity and frequency, and it needs to go that way so that we can deliver the baby. If labor was a negative feedback loop, pregnancy would last indefinitely, right? And that's not going to work out.